Dear friends, this lesson regards greenhouse innovative covering materials. My name is Giuliano Vox and I come from the University of Bari in southern Italy. The quality of a covering material depends on its radiometric and mechanical properties. The capacity of the covering material to modify the greenhouse microclimate strongly depends on its radiometric properties, mainly the transmissivity. The transmissivity in the solar range affects greenhouse temperature. The higher the transmissivity in the solar range, the higher the greenhouse temperature. At the same time, the lower the transmissivity in the long-wave infrared range, the higher the greenhouse temperature. Another parameter to be considered is the transmissivity in photosynthetically active radiation range, because plant photosynthesis depends on this parameter. Glass is a traditional covering material. It is used as float glass, hammered glass, or low-emission glass in greenhouse covering. It has a lot of positive properties: high transmittance in the solar radiation range and high greenhouse effect. But at the same time, it has a high weight, high cost, and fragility. Rigid plastics are good covering material too. Polycarbonate, PVC, and PMMA are used as covering materials. They require lighter and cheaper support frame in comparison with the glass, but do not maintain performance over time as glass. Over the last decades, plastic films have been introduced as greenhouse covering materials. The real advantage that they present is that they require a very light and cheaper support frame. The problem is that they have to be replaced every 3 or 4 years. What development can we expect for the greenhouse covering materials? Greenhouse films are materials suitable for the application of innovation, since they can include additives able to manipulate solar radiation. With this aim, recently several materials have been developed: photoselective films, photoluminescent films, UV-absorbing films, and air-blocking films. These films work manipulating solar radiation. If, for example, I want more compact plant, I can use films that favor blue radiation, because blue radiation favors more compact plant. Also, red radiation affects plant morphology. For example, red radiation is now enhancing shoot length and seed germination. Another parameter that can be used is the red-far-red ratio. If this ratio is high in comparison with the open field condition, is able to produce short and compact plants. If this ratio is low in comparison with open field condition, this is able to increase shoot length. Covering material able to produce the effect that we have mentioned before are the photoselective greenhouse covering films, since they can incorporate pigments that are able to modify the solar spectrum. Other materials able to manipulate solar radiation are the innovative photoluminescent plastic films that absorb solar ultraviolet radiation and shift them into photosynthetically active radiation range. A research carried out years ago showed that rose plants grown under photoluminescent film were more productive and the flowers were of a higher quality. Here I will show the results of the application of photoselective and photoluminescent films at the experimental field of the University of Bari. We applied two photoselective films made in order to change the RFR ratio. Besides, we used also three photoluminescent films that were used to move ultraviolet radiation in red, blue and red-blue radiation range. A film based on polyethylene was used as control. In this slide, we can see the transmissivity curves of two photoselective films and of a non-photoselective film. We can see that the two photoselective films in red and green decreased the red-for-red ratio from 1.13 to 1.01 and 0.93. So, we expected by the application of this film that the plant grown under the photoselective films should have higher shoot length. We can see in this slide the properties of the luminescent film that we used in the test. The red film moved ultraviolet radiation to the red radiation band. The blue film moved ultraviolet radiation to the blue band, while the red-blue film moved ultraviolet radiation to both blue and red bands. We expected that the plants grow under the blue film should be more compact, while the plants grow under the red film should have higher shoot length. This slide shows the results of the application of the two photoselective films. We can see that the plants grow under the film green 4% that had the lowest value of the red-for-red ratio showed the highest value of the shoot lengths. So, this is what we expected from the application of these photoselective materials that changed the red-for-red ratio, decreasing its value in comparison with the open field and the environment under the polyethylene film. This slide shows the results of the application of the selective and luminescent film together with the results for the open field and of the environment created by the polyethylene film. We can see that the highest shoot length was obtained under the selective films, while among the luminescent films, the highest shoot length was obtained under the red emitting film, and lower value were obtained under the blue luminescent film. And these results doesn't mean that higher shoot length is better than lower shoot length, but it demonstrates the capacity of the film of regulating plant growth in place of chemicals. Greenhouse covering material can be used as alternative to chemicals for pest and disease control. In fact, UV-absorbing greenhouse film creates a radiation environment unfavorable to harmful insects. On the other hand, UV radiation reduction can limit the entry of insect pollinators. So, about the use of these materials, there are conflicting opinions. About the result of the application of the UV-absorbing films on the production, We can say that in Israel no significant differences were found on growth, yield, dry weight in tomatoes production. In Greece, the application of these materials on eggplants showed that similar results were obtained in comparison with the standard covering materials. In Spain, an increase in tomato yield was reported when UV-absorbing films were used. Another useful application of materials able to modify greenhouse microclimate by acting on the solar spectrum is represented by the near-infrared blocking films. These films are able to reduce this radiation that is useful only to increase greenhouse temperature. So, as consequence, they reduce greenhouse temperature peaks. This is useful especially in warmer periods and in the southern regions of Europe. For example, in Mediterranean areas, they can reduce the peaks of temperature in summer, avoiding damage to the plants. We have to say that these materials do not reduce photosynthetically active radiation, so they don't reduce photosynthesis of the plants. At the end of this presentation, I want to thank you for your kind attention.